Okay, and let's start sharing the screen. Good. So last time we started working on powering an AC circuit. Okay, and that's going to be the last thing in chapter. Which chapter is the one? 21. No. 23. Chapter 23. Okay, and then we move to chapter 24. Let's get here the dates going on, and today is 28th of April, 9:42 Pacific Standard Time. Let's see, 28, 25. Let's take a look at our syllabus first, right? Week number, meeting number. Syllabus. Oh, here we go. We are writing here. No, sorry. We are writing here just after the exam. Oh, next Wednesday, the day after tomorrow is going to be a holiday, huh? So let me put the AC. Is this AC circuit? Okay, this is AC circuit. What's going on here? AC circuit 2. Yeah, just a little bit of AC circuit. Should be 23 and 24. Okay, so here we go. 28th of April. And next exam so far is the 21st of May. A little bit less, let's see. 1, 2, 3. 3 weeks and a half from now. That's the situation, right? I don't want to boldface this one. Here you go. I don't want to boldface this one either. Let's leave it this way. Okay, and now let's go back to the lecture. Okay, now one more thing, right? We need week number 12. Week number 12, meeting number. Meeting number 18. Meeting number 18. That's what we have. And let's continue what we were doing before. It's just the power, and then it's gonna be quick. Not much, not many things. Here you go, just to remind you what we did before. We are going to use the same equation for the power of the DC circuit to find out the power in an AC circuit. V times I, R times I square, or V square over R. Okay. And in the case of a DC circuit, the instantaneous power is constant because V and I are constant in time, are constant in time. However, in a AC circuit, the instantaneous power must vary in time because V and I are a function of time. So here, if we want, right, to have a result, a power that is constant, we must define, we must use, well, let's put, when we usually have a quantity, right? When we usually have a quantity that changes in time, right? When we have a quantity that changes in time, we usually define an average value for this quantity. And that's what we do. And that's what we do. That's what we do for the power of an AC circuit. Okay? There is just one problem. There is just one problem. However, the regular average, right? However, since the voltage and current are a function, are a sinusoidal, function, are sinusoidal functions, right? The regular average value of a sine or cosine ends up being equal to 0. And I can prove that rather easily for you. All we have to do is to plot a sine function. Okay, here you go. I'm going to do that in Excel so you can see what I mean. You please paint. Here you go. Let's see. I want to put N here, right? I'm going to put T here, and let's put. I'm going to start with the V, with the voltage. The current would behave rather in the same way, right? N for N equal to 0, N stand T is going to be equal to 0 as well, and I'm going to write down a function of time. Let's say 2 volts times sine of 2 pi times t. Okay. Everybody knows how a sine function works. Right here, I'm gonna put the number of points that we have. And let's see, I don't want 2 pi, let's see. I want 2 pi divided by 10. Let's put 2 pi divided by 10. And if it works, we stick to that. If it doesn't work, we do something else. Even better, I don't need to put it here. All I have to do is to put it right here. Okay, so here you go. This one divide by 10. Okay, T here is going to be in seconds. V here is going to be in volts. Let's see if I got it right. Okay, so it looks like we have to to be a little bit, let's put 20 instead. Sometimes those things are going like in a, okay, looks like we got it. We got it this time. Okay, 0, yeah, looks like we have a good one now. And we want a full cycle. At least a full cycle we want. Okay, so we have a full cycle here. After 20 data points, we have a full cycle. This number is 0, basically. 10 to minus 16 is, for all practical purposes, it is 0. Okay, and I'm going to plot my V against T. And you are going to see here, nice sine wave, right? Note that this sine wave spends exactly the same amount of time in the positive and in the negative region. This area here is going to be equal to this area, right? This area here equal to this area, and so on. For a full cycle, if we take an average of this function, we are going to get 0. Because the positive here is going to cancel the negative here. The positive here, of this area is going to cancel with the negative in there. So that's the problem that we encounter when we deal with average values of an AC circuit. Okay, so here we go. I'm going to get this thing. Okay. However, since the voltage and currents are sinusoidal functions, the regular average value of a sine cosine ends up being equal to 0. See below. Okay. Here you go. Here's the function. For this reason, we must, well, not we must, but we define a different type of average. We not what we define, but we use a different type of average. Okay. The so-called square root of the average of the square of the square. Okay. First, we square the function. Then we take its average. And finally, we take the square root to ensure we end up with the correct unit. Okay? With the correct units. And I want to put this one. The average value, okay? And I'm going to use annotation that's widely used out there, okay? What I'm going to do. Note it from the above. Note from the above graph that, here you go. We use this triangular bracket right here to denote average. We usually do that. Triangular bracket. We can extend this triangular bracket like that. Nope. It did something that I didn't want it to do. Let's see, let's try now again. Yeah, okay, now it did what I wanted. V naught is a constant. So the average value of a constant is going to be the constant itself. And then we have the average value of a sine function that ends up in being equal to 0. 0 times a non-zero number is going to be 0. 2 more students coming, okay? For the reason, we use a different type of average, the so-called square root of the average of the square. To obtain, here you go. To obtain this average, also called the root mean square value, RMS, we do the following. Right? 1, first we square the function. Then we take its average. And finally, we take the square root of the above to ensure we end up with the correct units. Okay? So the situation now is the following, instead of VG, let's just call it just V. Okay, and the situation goes like that, We follow exactly what I mentioned here. First, start with this one here. Okay, first we square the function. Here you go, that's the first step. Okay, then we take the average of the square of this function. Take the average, going to be just like that. Like that, right? Just like before, we're going to have something like that with a but then I have to square those right? The average of a constant is going to be the constant itself, but now the average of a sine square is no longer going to be 0 for a very important reason, and you will be able to visualize that in my graph. Okay. Here you go. And now what I'm going to do, I'm going to put it v squared here, right? The v between parentheses is the unit. Page layout, no. Home must be here. Superscript. Yeah, good. All I have to do is to square the column for V, and whatever with the negative value is going to become positive, right? Let's plot this new function now. We're going to see, here you go. That's how it looks like. I'm going to do better than that. Let's see. I'm going to put this one. Yeah, here you go. Better. So now you can see that it never become negative because you're squaring any negative numbers. Okay. And then what's the next step? Okay. The next step is to take the average of this function that you see right here. When you take the average of this function, it's possible to prove it mathematically, but it requires advanced calculus. What we end up finding out is that okay, the average value of the sine square, right? Let's take a look here. Wait a minute. I gotta do something else. There is a little boo-boo here. I have to take out this. Remember, I'm taking out the average of the sine, right? Not the average of this 2 times sine, right? So here you go. Now we got it right. Okay, the value is going to be between 0 and 1. Okay, and the average value of this function is going to be half. Okay, it's going to be half. So the average value of my sine square is going to be half. Did you do everything yet? Not yet, right? Not yet. So here you go. We start with the original function, right? That's the original function. First, we square the function. Here are the steps. And then I'm going to square the function. Then we take its average. And by taking the average is finally, we take the square root of the above to ensure we end up with the correct units. And then, we gotta take the square root here. And I'm gonna call that root mean square, RMS. And is the square root of this value. Okay. That's what we get when we take the root mean square value of a sine function. The root square mean value of a sine function is going to be 1 divided by square root of 2. Okay. That's what we do. We have the same for the current. Have the same for the current. I'm not. I'm not of the square root of 2. Okay. When we combine those two results for the power, what we get? Let's go back to the power. Equation for the power right in here. Right? We have to take the root mean square value of the power. power. We get RMS for the voltage, RMS for the current. And then what we get, just substitute each one that we have right here. Okay, and we have V naught I naught divided by the constant 2. That's the special type of average that you have to keep in mind. Okay, the same applies to voltage and current. So if we're dealing with AC circuits, there are some multimeters out there that they cannot keep up with the voltage or measurement of the voltage of the current. Okay, because sometimes the voltage and the current is changing so quickly that you cannot see with your eyes the time variation of the voltage. So what those multimeters do? They report to you the root mean square value of the voltage or the current. And that's what the RMS value comes from. Okay. So we are done with this section. And I want to go back to the chapters that we covered. Let's see, I'm gonna get that. I get it from somewhere else here. AC circuit, okay. That's the one. That's what we did for AC circuits. Okay, we went back to chapter 20 because chapter 20 covered the alternating current with a resistance, right? We did AC circuit for a capacitor only, for an inductor only, and for RLC circuits for capacitance, for resistance, inductance, and capacitance. Okay? RLC circuits. We're not going to do resonance. Let's see if we have time to do that. If we have time, we go back. We definitely were not going to do that because that's for a more advanced course in physics. And I have to, let's see. I gotta erase that part. Okay, did you get it? Do you understand how you got the average? Okay, we just plotted in this graph and we get the midway between 0 and 1, which ends up being half. There's a more strict way of deriving that mathematically, but we don't do that here because it requires integral calculus. Differential and integral calculus. We do this derivation in the physics 38 course that I teach. And now we are ready to get into the next topic, which, notice that everything that we're doing here is consequence of what we covered previously, right? Notice that. Let's notice that everything we are doing here builds up on what we covered previously. For this reason, all right? For this reason, you must understand the previous chapters to master what is coming next. Okay? So the situation goes like that, Let's summarize what we have done since the beginning of the semester, right? First, I defined something that is called an electric charge, a basic quantity. You must believe in the existence of this quantity. You must believe in the existence of this quantity to understand what comes next. Okay? Then, what did we do? I told you that electric charges exert forces on each other. You know, the concept of force is something that was introduced in physics 6, in our previous physics course, physics 6. Okay? And of course, this concept depends on the idea of charge. After that, I came up after that. We came up with a far more abstract concept that is related to the electric force, the electric field. Okay, related to the electric field. Related to the electric field. We have the electric potential, energy, and the, let's see, not related to the electric field, relate to the electric force, okay? We have the concept of electric potential energy. Likewise, related to the electric field, we have the concept of the electric potential. Electric potential energy, electric potential. And then what else did we do? Okay, then we started talking about certain important electrical devices. Electrical devices, the capacitor and the resistor. Capacitor and the resistor. Both devices use the concept of electric field and electric potential. And then I introduced you the idea, of electric circuits powered by a battery of constant voltage. Okay? To the idea, powered by a battery of constant voltage. Constant voltage implies constant current. Constant voltage implies constant current. Okay. Let's take a look here. We're just summarizing what we have been doing throughout the semester, right? Let's take a look at the chapters here. Here you go. Electric force in electric field, electric potential energy and electric potential, electric circuits. Okay. In the idea of electric circuits, I introduce you to the idea of electric current, right? This is the idea of electric circuits powered by a battery of constant voltage. Constant voltage implies constant current, which is the next important concept, the concept of current. Okay, then I told you that a current, that associated to a current, we have a magnetic field, okay? We have a magnetic field. The current is a source of magnetic field. By the same token that an electric charge is the source of an electric field, a current is the source of the magnetic field. Magnetic field represented by the letter B. Okay, that's, you go. And that's this chapter, right? Chapter 21. Then I introduce you the idea of electromagnetic induction, okay? Another law of physics. Then I introduce to you the idea of electromagnetic induction. You know, a varying magnetic flux induces an electric current in a circuit. That's the key idea behind that. Let's see. Electromagnetic induction. Yeah. Let's see if he already moved forward. We actually can move past that. Okay. Let's see if he did that here in this chapter. Doesn't look like he did. No, he didn't. But that's what we are going to do now. We are going to extend into this, onto this idea of electromagnetic induction. Okay. Using the idea of electromagnetic induction, using the concept of electromagnetic induction. Now let's put EB, right? B for magnetic induction. I introduced you to a very important device, the generator. The generator. And now that we have a generator, we can do some neat things with the generator. Okay? Implies, okay. Okay, I'm going to put it here between parentheses, Ampere's law. Ampere's law. Okay, and that's going to be the Faraday's law. Faraday's law. Here at the top, here is the Coulomb's law. Coulomb's law. There is one more law that we didn't give it a name to it, but it's the Gauss's law for the magnetic field. Coulomb's Coulombs slash Gauss's law. 1, 2, 3, 4, 10. 10 concepts so far. Let's see if I'm missing something else. Because, okay, now, the last thing that we saw, was a different type of circuit called the AC circuit, where the power source is the generator. Okay? What we are going to do now, we are going to elaborate on this idea of electromagnetic induction. What we are going to do now is to elaborate on the idea of electromagnetic induction. Okay? There is more to it than what I have told you. There is more to electromagnetic induction than I let transpire. Okay? There is more to electromagnetic induction than I let transpire. Okay? And this idea of electromagnetic induction is going to result in the concept of electromagnetic waves. Okay? And this new take on electromagnetic induction is going to result in, is going to explain, right? Explain the existence of electromagnetic waves. Electromagnetic waves. Okay? That's what we have done up to now here during the entire semester. I also told you that an electric current, right? Is the source of a magnetic field. That's right, just improving here. When you think of the electric charge is the source of electric field, a current is also the source of a B field. And how do you do that? Okay. Again, we are going back to the idea of electromagnetic induction. Let's see here. Number 12. So what I can tell you that, and let's see, did I put it here? Okay, I'm going to put chapter 24, electromagnetic waves. Electromagnetic waves. And electromagnetic waves rely heavily on the equations of electricity and magnetism. And it's very difficult to emphasize the importance of this material. It's very difficult. It's because of this whole treatment, this whole theoretical treatment that I'm presenting to you, that we today have cell phones, that today we have telecommunications. Not just telecommunications, but electricity as well. What we are teaching in this course is the foundation of modern society, okay? Without this knowledge, we would not have electric circuits, electric light, electricity, telecommunications, etc. Just imagine living in a world without electricity. Okay. Think about that. Without this knowledge, without the knowledge of magnetic force, for instance, right? Without the knowledge of magnetic force, we could not build electric motors, right? Without the understanding of magnetic force, we could not, never have created a cathode ray tube that were the screens initially used in the early TVs and computer displays. Without the understanding of electromagnetic induction, I'm just emphasizing how important this thing is, okay? We would not be able to generate electricity. We would not be able to generate AC electricity. AC current. AC current. It's because of this phenomenon that power stations are capable of generating electricity, are capable of generating electricity and cables, right? And transmission cables to transmit this electricity through long distances. Through long distances. And finally, okay, it's because of electromagnetic waves. Okay, without one more step here before we get into the idea of electromagnetic waves, right? It is also because of electromagnetic induction that we can create electromagnetic waves. Finally, it's also because of electromagnetic waves that today we have long-distance wireless communications. Our cell phones use this concept. Our cell phones would not be possible without electromagnetic waves. Our cell phones would not be possible without electric circuits. And everything goes back to the law of electromagnetic, the laws of electromagnetic, of electricity and magnetism. And I'm going to, right? And I'm going to remind you of those laws. Don't forget, you have to memorize those laws for the rest of your lives. Gauss's law of electricity. The one that involves the electric flux. Gauss's law of magnetism. It doesn't have a special, Gauss's law of magnetism. There is no magnetic monopole. There is no magnetic charges, okay, or monopoles. All you have to do here is to change everything that's E, we change to B. And the right side is going to be 0 because there's no magnetic charges. And then we have Ampere's law. Electric current generates a magnetic field. Like like that. And then we have the Faraday's law of electromagnetic induction. You know, the induced electric potential is equal to the change in the magnetic flux multiplied by the number of turns of your electric circuit. There is, there is something about this law here that's not completely correct. Okay? There is something about this last law that is not completely correct. Okay? There is more to it than induced current. There is more to it than induced voltage. Okay? There is more to it than induced voltage and induced current. And that's what the idea that I want you to understand. Okay. Also, there is something about Faraday's law, but not Faraday's law, Ampere's law. Ampere's law. That's not completely correct either. Okay? I'm not telling you the whole idea, the whole thing. I'm telling you part of it. Also, there is something about Ampere's law that's not completely correct either. Let us start with Faraday's law first. Faraday's law first, and then we address Ampere's law. Okay? At this point in time, okay, so what I have told you about Faraday's law. Okay? Let's start with the equation of electromagnetic induction, which is Faraday's law. Okay, you already know the following. I'm gonna put it like that. You already know the following. A change in magnetic flux induces an electric current. Oops. A change in magnetic flux also induces an electric potential that powers the above current. Then I have, like I mentioned to you before, I have some news for you. This is not the whole story. This is only part of this story. This is not the whole story, but only part of it. And the story is much more interesting than that. And the story is much more interesting than that. Okay. What is induced? It's not just an electric current. Just an electric current. What is induced is not just an electric potential. Okay. What is induced is something else that is far more genetic and this something else, and it is this something else, and it is the something else that gives rise to the induced current, and the induced electric potential. Okay? Think about that. Okay? And this is the generic idea. It's something else that you already know. It's something else that you have already seen before. Okay? And this something else is a concept that you have already seen before. You have already seen before. Okay? It is this changing magnetic flux induces, instead, I'm going to put in capital letters, an electric field. Okay? It's an induced electric field. That's how you are supposed to interpret this law. And it is this induced electric field that gives rise to this induced electric potential. And it is this induced electric potential that gives rise to an induced electric current. Okay? That's the qualitative idea that you have to have in your mind. And it is this induced electric field that gives rise to the induced electric potential. It is, it is also this induced field that gives rise to the induced electric current. Okay? And I will be able to illustrate that for you so you can have a better idea, a more clear idea. But before we go into that, let's take attendance and take our little break. Okay? 28th of April. Abir Ahmad, are you there?
Yes, I'm here.
All right, thank you. Nestor
Here.
Alvarado. Thank you,
I'm
Nestor.
here.
Monte Ambarchian.
Here.
Thank you. Next, Isabella Ballesteros. I don't see Isabella here. Justus Bowden. Justus, okay. Justus seems to be here. Thank you, Justus. Alexandra.
I'm here.
Thank you, Alexandra. Benjamin Carvajal. Good. Next is Elizabeth Castellano. Looks like Elizabeth is here. Next is Natalia Córdoba. Next is Jacqueline Delgadillo. Hello, Jacqueline. Looks like Jacqueline is away from her computer. Next is Jenny Diaz.
Here.
Thank you. Valerie Diaz.
Here.
Next is Juan Escalera. Hello, Juan. Thank you. Next is Bianca Eloki.
I'm here.
Thank you, Bianca. Edwin Gonzalez. Thank you, Edwin. Ellie Gonzalez.
Here, Professor.
Thank you. Manuel Hernandez.
Here, Professor.
Thank you. Samantha Hubert. Yeah, Samantha is not here. Next is CJ Joseph Hutton. Okay, no CJ. Amber Lopez. Well, I don't see Amber. Next, Arely Lopez. Okay, thank you, Arely. Next, Genesis Lopez.
Here.
Thank you, Genesis. Mary Michaelian. Okay, I'm gonna put a star here, Mary. Okay, now it's Galia. Okay, thank you, Ramon Olivares.
Here.
Thank you, Ramon. Next is Taylor Thorne. Jacqueline Delgadillo. Let's see. Okay. Taylor, are you there? No.
I'm here.
Are there? Okay. Thank you. Jeremy Pittman. I don't see Jeremy here. Next is Stephanie Ramos.
I'm here.
Next is
Sorry.
who is that?
No, nothing. It's just my voice. I'm a little sick.
Okay. Leslie is there?
I'm here.
There you go. Is Leslie there? Leslie Rios?
I'm here.
Oh yeah, you're very low. Yeah, okay. Thank you, Leslie. Jason Strait.
Here.
Thank
Here,
you.
Professor.
And last, right, but not least, Hema Torres. Okay, thank you, Hema. Let's see how many students we have. 24. Okay. Mary, one more chance for Mary. Hello, Mary, are you there? Michaelian?
Yes, I'm here.
Okay, thank you. So now the numbers match. Good. So let's go for our break. It's going to be break 10:45 a.m. to 11 a.m. Okay? So see you in the next 15 minutes. Stop sharing. Okay, I'm back here. And let's continue. Okay, so now I'm going to give you some illustrations to help you understand this concept, this idea, but it's closely related to the induction of electric current. If you can visualize the induction of electric current in a circuit, you will be able to visualize the induction of the electric field. Electromagnetic waves. Okay, so here you go. Electric field induction. Now, what was electric current induction, or what was electric potential induction? Now it is something far more genetic. Is the electric field induction, right? So the idea goes just like that. Now you have this conducting wire, right? in a magnetic field. And if the magnetic field changes in time, there will be a current induced in this conducting wire. Okay? But we do not have to have a conducting wire to have induction. Here you go, here's the wire. If the magnetic field is increasing as time goes by, the electric current will be induced in a counterclockwise direction. Okay, but what is powering this induced current is actually an induced electric field that looks just like that. Okay? You can even remove this wire and the induced electric field is still going to be there. Okay? And the induced electric field is going to have the same direction as the current, as the electric current. It's going to be circulating as well in a counterclockwise direction. Okay, so here you go. We have an electric field induced everywhere in space where the magnetic field is changing, we end up having an induced electric field, this invisible quantity that's difficult to measure, even today. Okay, in order to measure the electric field in space with no electric current, with no wires whatsoever, you have to buy an expensive device that costs at least $3,000. Okay, so here you go. Did you get the idea? So here you go. I'm going to copy and paste some of those drawings here in the notes. So what was written in terms, what was written in terms of voltage, of electric potential, right? Electric potential and current must be rewritten in terms of the induced electric field. And the way we write that is like that. Okay? This is a more generic format of Faraday's law. Of Faraday's law. Okay? Note that, you know, it's what you see here is kind of similar to what you have seen before for the magnetic field, right? You have a loop, an imaginary loop in space, but instead of a magnetic field, you're going to have an electric field, an induced electric field. What is in the right side? Right-hand side is going to be a change in flux, magnetic flux. Whereas for the other one, we have an electric current. An electric current is creating this magnetic field in the Ampere's law. Whereas a change in magnetic flux is inducing an electric field. Delta L here is for the, like I said, it's for a pass, an imaginary pass, an abstract pass. So here you go. I'm gonna copy and paste some of those drawings that you saw. Not everyone, okay? So you have a pictorial idea of what is happening. Here you go. Changing magnetic flux induces. You already know that changing magnetic flux induces a current in a circuit. Here you go, conducting wire. But in reality, what actually happens is much more interesting. There is no need to have a conducting wire for electromagnetic induction to occur. What's actually powering the electric current is an induced electric field. So here you go. And this induced electric field circulates around the lines of magnetic field. You don't even need, like I said, you don't even need an electric conductor to have this induced electric field. It also can happen in free space. Here you go. In this drawing, I removed the electric conductor. In summary, a change in magnetic flux. I'm gonna erase field here. Induces an electric field, whether it is in free space, in a dielectric material, or a conducting material. And this induced electric field may or may not change in time. Okay, and now you must have this picture in your head. You create a magnetic field or magnetic flux that's changing in time, and this magnetic flux is going to induce an electric field. Okay? So that's the ultimate interpretation that must be given for the law of electromagnetic induction in its broadest possible sense. Okay, here you go. I want to write that down here for you. That's the ultimate interpretation that must be given for the law of electromagnetic induction, which is the broadest and most, which is the broadest and most genetic one. Remember, but also remember, if you introduce an electric conductor in this magnetic field, the induced field will power an electric current in the conductor. So now we can even say that we have two types of electric fields. Okay, an electric field that's generated by a charge distribution, Gauss's law of electricity, and an electric field that's induced by a changing magnetic flux. Okay? We can also say that we have, so far, okay, that's not the whole story yet, because we can always say that we have only one type of, for now. This is not the whole story. Don't forget, this is Ampere's law, right? Remember that I told you that Ampere's law is incomplete. We didn't cover Ampere's law yet. We're just adjusting the ideas of our Faraday's law. Only one type, and so far, I'm going to put it here. So far, only one type of magnetic field, the one that is induced, let's say, or produced, right, by a current. Okay, the first type of electric field. Let's see, Bianca. Okay, someone is turned on accidentally their mic, right? Let's see. The first type of electric and magnetic fields are, generated by static sources. Okay. First type of electric and magnetic fields are the ones generated by static sources. Static charge or static current. Static charge or static charge and static current respectively. We call them the electrostatic field. The electrostatic, we call them the electrostatic field. That would be the electrostatic field right in here, and the magnetostatic field. Okay, and the magnetostatic field. They're called electrostatic and magnetostatic because they do not change in time, okay? They are called static field because the sources, okay, do not need to change in time to create their respective fields. Okay? In the case of Faraday's law, something else has to change, right? Whereas in the case of Faraday's law, something else has to change. Something has to change. And that something that changed is the magnetic flux. Magnetic flux here. And if flux doesn't change, if the flux does not change, then the induced field is zero, right? If the flux doesn't change, I'm going to put it here. Delta phi, delta t is equal to zero. And the induced field is also zero. And the induced field is also zero. Like that. Put like that. Okay, and we can build up a table to a table so you can visualize that more easily. Okay, so here we go. Tables are very useful. And summarizing in table format. Okay. Types of fields. Electrostatic. The source is the electric charge. The source behavior is static, and the field behavior radiates from the source. Remember that? Either radiates from the source or converge towards the source. Magnetostatic, the source is the electric current. Source behavior is static current. And the field circulates around the current, right? And now we have the induced electric field. That's the new kid in the block. That's the new kid in the block. The source is a changing magnetic flux. Source behavior, the current is dynamic, it changes. And the field, the induced field also circulates around the flux, also circulates around the flux. And then we have the final one that we didn't discuss yet. Okay. What I want to do now, let's see, before we go talking about this one, by the way, did you see that they're talking about some power? Let me see if I find the news here. Yeah, they're talking about power outage there in Portugal and Spain and France too. And they're saying that maybe it's a cyber attack. Have you heard about that? They're in the States. This is in Portuguese, right? I thought it was rather, power outage in Europe, right? I just found out about that. And maybe a huge power outage bring parts of Spain and Portugal to standstill, even France. And hopefully it's not a cybernetic attack, Maybe it's just they causing transport chaos, and especially with this thing going on there in Europe with Ukraine, right? So let's watch that. Remember I told you we cannot live without electricity? That's what happened there in Spain and Portugal, causing chaos. If you know anything about that, let me know, okay? You heard about that, Benjamin? Okay. But did you hear that it could be like, a cybernetic attack? What they're saying? No, that's news to you, right? Okay. Yeah, so far all those news that I see here doesn't say that it's cybernetic attack. It's just this YouTube channel here that are suggesting there's a possible cybernetic attack, cyber attack, right? Let's hope it's not something like that, because if it is something like that, things are going to get very complicated. I find that many of the news in YouTube are, they put this headline just to attract your attention. And then when you go watch the video, it's nothing like that they mentioned, They abuse, right? Those channels in YouTube, they frequently abuse the headlines. Okay, so let's take a look at the book now, and electromagnetic waves, and then we still didn't cover the electromagnetic waves yet. Let's see, electromagnetic spectrum. Yeah, we have whatever I covered here is just not covered in the book, by the way. Okay, they just make that jump, saying that if you change the current, you can create an electromagnetic wave. But that's how the story goes. And I still didn't tell you the whole story. So let me tell you the whole story. Okay, and I told you, like I mentioned, I told you that there is an induced electric field, but there is also an induced magnetic field, okay? There is also an induced magnetic field. So like I said, the story is not complete yet. And now you can start to visualize what the electromagnetic wave is. It's still not complete, still not complete. But right now, right in here, you can start to have a glimpse of your electromagnetic wave. Think about that. We have a magnetic field that changes in time, most likely sinusoidal in time, back and forth, right? Just like a generator. You turn on your generator, you create a magnetic field around the generator that changes in time, and this generator induces an electric field as well. Just an electric field as well. And so far, what I have right now is just a glimpse of an electromagnetic wave. You do have electric and magnetic fields in free space. But like I said, the whole story is far more interesting than that. Okay? Sometime, in the mid 1800s, there was this guy called James Clerk Maxwell. Okay. Back in the mid 1800s, there was someone called James Clerk, right? Maxwell. Let's see, it's Clark or Clerk. Let's see. Yeah, it's Clerk Maxwell. That's right. One of the geniuses that make important contributions to science. He was a Scottish physicist and mathematician. He was looking at those same equations that I spelled out to you, okay? And he found that there was something wrong with them. There might be something wrong with them. Let me write them here. The equations that we have so far are the following. Actually, not that something wrong with them, okay? There's someone called James Clerk Maxwell who was looking at the equations of electricity and magnetism. And the equations at his time looked just like that. He already had this interpretation, right? And he was starting to think about those equations, okay? He looked at this equation here, and he was asking himself, if a change in magnetic flux induces an electric current, an electric field, can you have the same for the magnetic field? That's what he was asking himself, okay? It was at this point, that's what we call symmetry in the equations, okay? Maxwell was, let's write that down here. Maxwell was looking at the above equations. And he asked himself, if a changing magnetic flux induces an electric field, can we also have the opposite? Okay? Can we also have the opposite? Physicists, they like to think about that. They're trained to think about that. Okay? And and the opposite would be what? In other words, right? In other words, would it be possible that a changing electric flux for a change in electric flux to induce a magnetic field? That was the question that he was asking himself. Okay? And in reality, he found that yes. And the answer was yes. And the answer was yes. Okay? The next question now is which equation would carry this information, right? Here is Gauss's law of electricity, Gauss's law of magnetism, Faraday's law of induction, and Ampere's law. Okay, well, it happens that it was the Ampere's law that was incomplete at his time. It was, here you go. I'm gonna, here, right here, it was this term here that was missing from the Ampere's law. Maxwell discovered that there was a term missing from the Ampere's law. Ampere's law. The term was from Ampere's law. That was the term. And now we do have that change electric flux can also induces a magnetic field, just like a changing magnetic flux induces an electric field. Okay, this suggested, that both an electric and this suggested both a changing electric and magnetic fields were reinforcing each other. The next step was to conclude that we actually have an electric-magnetic wave, okay? And we do have nice simulations out there that you're going to see. The book itself has a simulation of this type, an illustration, right? Simulating this thing. Let's go get here. Here you go. In this case, what do we have here in this case? In this case, we have a generator right in here, okay? And this generator has two antennas. It's not a closed circuit, okay? You don't have to have a closed circuit to have a current flowing through in this circuit, okay? At time t equal to 0, the voltage of this generator is equal to 0. A little bit later on, you have charges in the positive and negative. We have positive and negative polarities at the antenna, okay? Because the voltage here is 0, the electric field associated with this device is going to be 0 as well. But as the charge builds up in this generator, the electric field increases. Okay, notice the direction of the electric field is from the positive to the negative direction, right? Here you go. Here Here's the electric field vector. And this generator goes through cycles, right? First, you have positive on one side, negative on the other side, and then it reverts back to zero. And then the charges invert the direction. See that? Producing an electric field that points in the other direction, and so on. Okay? Because the generator is changing in a sinusoidal fashion, the electric field is also going to change in a sinusoidal fashion. Furthermore, because this electric field is changing in time, it will also induce a magnetic field that's going to be tagged along with it. Okay, let's see if we have, yeah, right in here. That's the illustration that you have to keep in mind. Okay? This type of device is what we called electric dipole antenna. Okay? Like I said, you don't have to have a closed circuit here. You can leave just like that, and still you're going to produce an electric and magnetic fields. That's how antennas work. But this antenna here is what we call a transmitting antenna. Okay, it produces an electric field, and the electric field, because the electric field is varying as time goes by, it's also producing a magnetic field that tags along with it. And this guy propagates away from this antenna, just like a wave propagates in a string. Okay? Maxwell also found everything I'm telling you here, folks, is very, how to say, in a very qualitative way. Okay, if you want to do the mathematical treatment, it requires higher levels of math. Okay, so you have to understand the story. You have to believe in this story. Okay, and if not even necessary, you have to memorize this whole story that I'm telling you here. And because of the sinusoidal change in the electric field, this thing will start to look like a wave that propagates away from this antenna. Okay, and that was the thought process that Maxwell went through. The next question that he asked himself is, what is the speed of this wave? That's the next question that he was asking. Okay. Let's see if I have something like that here. Yeah, I have my own. Okay, here you go. I have even better illustrations here. Here you go. That's the antenna, right? My transmitting antenna connected to two wires connected to my generator. I think this illustration is better because it has more steps than the other one that's shown in the book, okay? So initially at time t equal to 0, the voltage of this generator is 0. The voltage of the generator 0 means that you do not have any charges at the end of this wire. As time goes by, charges start to build up at the end of this antenna. Positive charges on one side, negative charges on the other side. Just like your regular battery, right? The only difference is that your regular battery has only negative charges on one side and positive charges on the other side. However, those charges, they do not change as time goes by. In a generator, they do change. Okay? Further down the line, you have more charges build up. Okay? Even more charges build up. Those charges are oscillating. And now, here you go. They start to go back to its original charge distribution. Decrease, decrease. All of that is changing according to a sinusoidal relation. Now the buildup of charge is going to become 0. It's going to become neutral. Going to have a neutral charge distribution by generator, and then the direction of the charge is going to change. Remember, we initially had a negative charge here on the left side, but now that we are going through the other side of the sine wave, we are now going to have a positive charge build up in the left side of the antenna. Okay? Here you go. More charge, and then the cycle is closed and repeat itself, okay? And repeat itself. Do you picture that? Okay. That's what we call electric dipole antenna. Electric dipole antenna, okay? We go. And this electric dipole antenna is generating an electric and magnetic fields that propagate away from this antenna. Let's write that down, that everything that we have said so far. So here you go. Electromagnetic wave, okay? The best way to visualize, there are two ways to visualize. There are two ways to visualize an electromagnetic wave. So far, I showed you only one type, okay? There are two ways to visualize the production of an electromagnetic wave. One, first, with a generator attached to two pieces of conductors. Two pieces of conductors creating an open circuit. This type of device is called an electric dipole antenna. Okay, electric dipole antenna. And there's a reason why we call it an electric dipole, right? Because we do have an electric dipole here. Do you see that? Negative charges on one side, positive charges on one side. There's a very good reason we call it an electric dipole antenna. It's called an electric dipole antenna. It's called an electric dipole antenna because we have charge distributions that, because we have a charge distribution that reflects that of an electric dipole. Okay? And I'm going to copy and paste my electric dipole there. Here you go, my electric dipole here. Copy and paste. Maybe. Okay, here you go. Here's my electric dipole antenna, right? I'm gonna write further right. This electric dipole antenna generates an electric field that changes in time nearby it. The change in E field induces a B field, creating an electromagnetic field that moves away from the antenna. Okay? The other way. And second, right? Second, also with a generator, attached to a current loop. Okay? This current loop that's closed, by the way, that's closed. Attached to a closed loop, right? Let's put it this way. To a closed loop, whereas the generator creates a current that changes in time as well. This type of device is called not an electric dipole antenna, but a magnetic dipole antenna. It's called a magnetic dipole antenna because we have a current distribution in a closed loop. In a closed loop that reflects that is a magnetic dipole. And I'm going to illustrate that as well. Here you go. Two different types of current. Here you go. Here's my loop. My generator is somewhere here along this loop. Okay? I didn't illustrate my generator, but I can do that. Let's see if I can do that. I'm going to illustrate that for you. Here you go. I'm going to put my generator. First, I have to make it smaller. Group them. Here you go. I have to make it smaller. Too small now. Yeah, okay, that's good. We're getting there. We're gonna make it a little bit more. Here you go, like that. And now I can put it here, right, in the circuit, in my circuit. And I'm going also to do something else. Let's see, I can do that. No color. No, I wasn't able to do that. Fill, I'm gonna fill. Here you go. Okay, here you go. Now I have it. Okay? A generator, you have a loop attached to this generator. In the next drawings, I'm going to remove the generator to make the drawing simpler, right? And this generator powers a current that moves back and forth in this loop. Okay? Powers a current that moves back and forth in this loop. It's possible to have a picture view of, because we do have a current in this loop, this current is going to generate a magnetic field, right? There will be a magnetic field here pointing either towards you or into the board, right? There will be another magnetic field here pointing into the board or away from the board. Here you go. And that's what I have right here at this spot. See that? At this very instant of time, I have a magnetic field pointing towards you just by using the right-hand rule. Okay? As time goes by, and not only that, we also have a magnetic field that decreases the amplitude as you move further and further away from the source. Okay? And this current that's changing as time goes by, you wanna, we're gonna build in one direction, then it's gonna revert direction, it's gonna oscillate back and forth. The magnetic field is also going to oscillate back and forth. Here you go. The magnetic field also is going to oscillate back and forth. But each magnetic field line is also going to induce an electric field line around it. Okay? That's what you have here. See the red arrows? Okay? Not only at the top, but in the middle and the bottom. Okay? Circulating around the magnetic field lines. But note that the electric field here is going to cancel out with this other electric field here. Okay? Horizontal E field cancel. And the result is going to be just a vertical electric field. Not between those two magnetic field lines, but between the other magnetic field lines as well. Okay? And so on. Putting out together, notice that the E field also decreases from the left to the right due to the distance from the source, right? The outcome is going to be a downward component of the E field that prevails. Okay, so here you go. Do you see that? This electric field here cancels out with this one. But because this electric field is closer to the source, when they cancel with the other one, we are going to have a net field downwards. The same thing happens with this one and the other ones. Okay, here you go. Whenever the current loop changes direction, right, at some instant of time, the current loop is going to change direction. The magnetic field also changes direction, and the electric field is also going to change direction. And you're going to have this propagation of electric and magnetic fields. Two different types of antennas, okay? Here you go. See the magnetic field propagating, right? I can put more in there. And now the question that I made to you before, right? What's going to be the direction of this magnetic field, or of this, or what's going to be the velocity of these electromagnetic waves, right? This one. Can put another one right in here. Okay, so here you go. Electric and magnetic fields moving away, but they are also moving back and forth too, okay? We do have a simulation showing this type of behavior. And the book showed that to you. Okay, so here you go. And if we go back to that other simulation that we got before, 1150, right? Let's see if I can find the simulations. We have simulations of that in the internet. Let's see, generator. Let's get the generator here. Let's see. Okay, no, not this one. Is it? Okay, I got it. Hmm. Bear with me for a few minutes. Okay, so I have to go back here. Now, mechanics, oscillation and waves, standing electrodynamics, electromagnetic waves. Okay, here you go. That's how it should be looked into. Note that the electric field is perpendicular to the magnetic field. I'm going to put this link, and it's moving from the left to the right, right? Which presumes that the antenna is farther to the left, further away to the left. Let's see if I can change that. No, I cannot change the velocity of the thing. Okay, so let's write that down, everything that we cover here. And I also going to copy and paste I'm going to need this guy here elsewhere. Okay, right in here. Good. Just to emphasize the fact that we must have a generator in this loop, in this current loop. And now I'm going to copy and paste it. Okay, here you go. Okay, here you go. Both configurations generate an electromagnetic wave for a simulation of this type of wave. Check the following link. Okay? Check the following link. Okay? And now, let's see, we have 4 more minutes. I want to take advantage of those 4 more minutes. Looking carefully at the equations, looking carefully at the equations. And the equations are, and the equation is the following. Let me copy them. Here writing the equations, okay? Here writing the equations. Note that very far away from the source, from the generator, we have no charge distribution, and no current. No charge and no current distribution. Which result in the following set of equations. Right? So here you go, following set of equations. This guy, the first one and the second one are going to be 0. No charge very far away, and no current here. See that? But only the terms of the magnetic and electric flux that changes as time goes by. Okay. Furthermore, note that we have a little term here in front of this guy. In the above equations, the term is the one that dictates the velocity of the wave. And I want you to do that at home, okay? When you go home, make sure you calculate the following equation. You know, what you have to calculate is not epsilon naught mu naught. What you have to, I want you to calculate is something like that. 1 divided by epsilon naught mu naught, but then you also have to take the square root of this term. When you do this calculation, you are going to get exactly the velocity of the light in vacuum. That is 300,000 kilometers per second. Go ahead and do that at home, okay? Get in your book what's the value of epsilon naught and what's the value of mu naught. Oops. And you'll find out that you're going to get exactly 300,000 kilometers per second. Remember, that's the term that dictates the speed of your wave, of your electromagnetic wave. It's 12 noon right now, and I want to take another break. Break 12 noon to 12:15 p.m. Okay? Any questions about that? I will see you in 15 minutes. Bye-bye. Okay, so we are back here. And that's what we have. Let's see. That's the book right in here, right? Nature of electromagnetic waves, speed of the light. Okay, speed of the light. And let's talk about the electromagnetic spectrum right now. Okay, so over in here, you know, he didn't do all that mathematical treatment that I did for you, okay? He didn't even mention that. And here you go. Here's one of the magnetic dipole, the antenna. Okay. Ship mass indicates that both straight and loop antennas are being used to communicate with the other vessels and of onshore equations, right? Stations. The loop antenna is the magnetic dipole antenna. The straight antenna is the electric dipole antenna. And now let's talk about the electromagnetic spectrum. Oh, by the way, before we go into that, right? The question is, how can we come up with what type of circuit, right? I didn't elaborate in the circuit. What type of circuit can we use? What type of circuit can we use to generate these electromagnetic waves. Okay, simple. It's an RLC circuit. An RLC circuit. I didn't mention that. We must have a generator. That loop that you saw there is just a generator with a resistor, an inductor, and a capacitor. Okay. A circuit with an RLC circuit can be used to generate these waves. Furthermore, we can also change the frequency and wavelengths of the wave by adjusting the capacitance and inductance of the circuit. Okay? That's how our antennas are done. Our antennas are done with an RLC circuit. And the frequency and wavelengths can be changed just by, and the frequency and the wavelengths of this electromagnetic waves can be changed just by adjusting the inductance and capacitance. The resistance doesn't affect, doesn't affect the frequency of the circuit. The resistance does not affect the wavelengths of the circuit. Only the intensity of the signal, the resistance affect only the intensity of the signal. That's why we study those RLC circuits. There's a little bit more to that than what I'm telling, okay? But overall is like that. And why I'm saying that? Because, okay, the wavelengths and the frequency of the circuit affects which type of electromagnetic wave we are talking about. Okay? There are all sorts of electromagnetic waves. Okay, the simplest one that require the least amount of energy are the radio waves. If you build a circuit that has a frequency of oscillation, okay, below 330 megahertz, current moving back and forth at the frequency of 30 megahertz or less, you generate what you call a radio wave. If you look inside your microwave oven, okay, you're going to see that this microwave oven of ours have devices that is capable of creating an electromagnetic wave between 30 megahertz and 300 gigahertz. Again, it's a circuit, okay, with a capacitance and a capacitor and an inductor. It would have a resistor there as well, which are tuned in such a way to generate, which are adjusted in such a way to generate a microwave within this frequency. Next time, go back to your, next time, check the back of your microwave oven to find out its frequency of operation. Okay, let's take a look at the internet. Here you go. Frequency of operation. Frequency of operation of a microwave oven. Microwave ovens operate at a frequency of 2.45 gigahertz. This frequency is chosen. Let's see if it's within that that value is 3.45 gigahertz. Yeah, it's well within, right? Is well within this range of frequency. This frequency is chosen for its ability to effectively heat food, particularly due to its interaction with water molecules within the food. Absorption by water molecule absorb electromagnetic waves with this frequency, which coincides to be in the microwave region of the spectrum. While some early microwave ovens use lower frequencies, like 915 megahertz, the current standard is 2.45 due to its improved efficiency and heating characteristics, okay? And then there's a few more electromagnetic waves there. Infrared radiation, anywhere between 300 gigahertz and 300 terahertz. And then we have the visible spectrum, which, by the way, is one type of electromagnetic wave, anywhere between 300 terahertz and 750 terahertz. If you do the math, you can convert this frequency into wavelengths, just like using that relationship from the course on waves. Okay, let's do that. Here you go. Do you remember that? In lambda wavelengths, right? Lambda divided by the period of your wave is equal to the velocity of the wave. But this equation can be rewritten in a different way as well. Instead of divided by the frequency, we can instead of divided by the period, we can multiply by the frequency and get the same result. Okay? So for the case of electromagnetic waves, this velocity is the velocity of the light, just like we had before. Here goes C, 300,000 kilometers per second. Okay. Kilometers per second. If you choose, for instance, a frequency of 750 terahertz, let's do this math. You know, a nice simple problem. What do you want? Let's see here. A nice simple problem to do. Find the wavelengths of an electromagnetic wave that has a frequency of 750 terahertz. Okay? It's a simple problem. Solution. Use the equation for the wavelengths and the speed of the light. Wavelength, frequency, speed of the light. Right? Substitute the value (300,000 kilometers per second) divided by frequency, the wavelengths, and then just get your calculator and find that out. Here you go. Let's do lambda is 300,000 kilometers per second. I'm gonna put 300 million meters per second divided by the frequency. 750 terahertz, 750 50 terahertz. What tera? Tera is how much? Let's take a look at tera. Giga, mega. Tera should be 10 to the 12. Let's see. Tera. Tera. Yeah, 10 to the 12. Okay. 10 to the 12. Then E to 12. And what we get? There's something wrong here. Yeah, definitely there's something wrong here. Let's see if I made the mistake. (300 kilometers per second) is more like 5, 6, 7, 8 meters per second. 3 times 10 to the 8 meters per second. And then we are talking about 750 times 10 to the 12 divide 10 to the 12 hertz, right? Hertz is 1 divided by second. We can rewrite that as being 7.4 times 10 to the 14th. 7.5 times 10 to the 14th. 7.5 times 10 to the 14th. Okay. And we end up with a, second here cancels out with the other second. With the other second. Right? 10 times to the 8 cancels out with 14. Then we get minus 6 meters. And then we have to do this math. 3 divided by 7.5. 10 to minus 6 meters is microns. There you go. I don't need the X anymore. And you have to do this math. 3 divided by 7.5 is around, 0.5 microns. I do not know why I got this value here. It's so odd. 300,000. 1, 2, 3. 1, 2, 3. Strange. Yeah, it looks like it doesn't like my notation here. That's the reason. 10 to the 12. Okay, now I got it. Now I got it. 4 times 10. There's more format here. Font number. Scientific. This is actually 4. Okay. 4 times 10 to minus 7. 4 times 10 to minus 7 is 400 times 10 to minus 9, which is nanometer, okay? So that what we end up having here is 0.4 microns, which is 400 nanometers. That's how we find out the wavelengths, if you know the frequency. Okay, so we didn't finish yet. We have more, right? The highest frequency ends up being the lowest wavelength, the shortest wavelength. Higher frequency, shorter wavelengths. Lower frequency, longer wavelengths. Okay, what else do we have? Ultraviolet. Ultraviolet radiation. Above 700 nanometers. Between 750 terahertz and 3 pentahertz. X-ray. X-ray is also an electromagnetic wave between 3 pentahertz and hectohertz, right? Deca, penta, peta, not penta, peta, exahertz. Kilo, mega, giga, tera, peta, exa, zeta, iota. Okay? And finally, gamma rays, 3 etahertz to 30 etahertz. The electromagnetic spectrum is usually depicted like something like that. The wavelength is below, the frequency is at the top. Our eyes can see only this small window in the electromagnetic spectrum. Very narrow window. That's what our eyes are capable of. Everything else, we need an instrument. We need an instrument that's either sensitive to gamma rays or X-ray or ultraviolet, infrared, or radio waves. And there are ways to build this type of instruments. 12:34, we have time, right? So we covered 24.1, 24.2, 24.3. So here we go. Students coming in. Here you go. Nature of electromagnetic waves, electromagnetic spectrum, speed of light. Now we're going to talk about the energy carried by an electromagnetic wave. Okay. For now, we're going to skip those two, okay? Energy carried by electromagnetic wave. We already know that both the electric and magnetic fields have energy, carry energy within them. We even derived an equation. We even derived the equations for their energy density. It's not difficult to memorize them. Remember that? The energy of the electric field, and then the density of energy of the electric field, and the density of energy of the magnetic field. They're very similar to each other. You have the same factor half. We have the square of the electric field, and it's just the constant that is slightly different. One is multiplied by the epsilon naught, the other is multiplied by the inverse of the mu naught. Okay? So, since an electromagnetic wave is made up of electromagnetic fields, the net energy density must be the summation of those two separate energies. Make sense? Right? So here you go. Like that. Electromagnetic density. Right? We can write it down, those two, and then there's more. Okay, there is a very important relation. We're not going to derive it here, but I'm going to just tell you. There's a very important relation that you must memorize. Okay. And this relationship, what's this relationship? Okay, for an electromagnetic wave, the energy density of the electric field ends up being equal to the energy density of the magnetic field. And now that we have this relationship, okay, we can simplify our equation. Since the energy density of the electric field is equal to the energy density of the magnetic field, look what that nice relationship we're going to get. I'm going to do the calculation for you, right? First, the half goes away. Half and half. Next, we pass the epsilon naught to the other side. And you should know what this relationship is all about, right? This relationship here is the square of the velocity of light. Okay? Like that. We can here write that in terms of the magnetic field. Is going to be divided by the square of the velocity of the light. And then taking the square root of both sides, E divided by C. But let's not forget that both the E and B, they are both a function of time, right? They're both a function of time. Not only they are a function of time, but they are changing in a sinusoidal fashion. Not only they are a function of time, but they are also changing sinusoidally. Okay, because of that, we can go back to our definition of root mean square, but now for the electric and magnetic fields. We have that the root mean square value of the electric field is the magnitude, is the amplitude of the electric field divided by the square root of 2. And the same thing applies to the magnetic field as well. Okay, but before that, right, I gotta do something else. I'm missing something here, right? Here you go. I missed a step here. Here you go. That's the step I'm missing. Because the B square is going to be equal to E square over C square. Oops. Let's do one more step. Like that. Okay. We can take the E square to the outside of the parentheses. Okay. And the C square is going to be given that by that value that you already know, mu naught epsilon naught. Okay, I gotta Yeah, this term here is going to become epsilon naught mu naught okay. Finally, we're going to have an even simpler equation, 2 epsilon naught mu naught is going to cancel out this mu naught, right? You end up with 2 epsilon naught inside the parentheses. There you go. And finally, the net energy density is going to be given by by this term here that you see. But let's not forget that the E field is a function of time. And if the E field is a function of time, so is the, 12:44. We have 6 more minutes to go, right? Yeah, 6 more minutes to go. Because the electric field is a function of time, of course, the energy density is also going to be a function of time. For this reason that we have to get the average of the square, the root mean square value. So the root mean square value of the energy density will then become, the root mean square value is no longer a function of time. There you go. The square of the root mean square value of the electric field. Which, by the way, is going to be given by E naught squared divided by 2. Divided by 2. We can here write that in terms of the root mean square value of the magnetic field, right? We have B naught squared. I think it's a good moment to stop here. 12:46. I have 4 more minutes. Any questions? Do you have any questions? Okay, so how many students do we have here? Okay, 14. That's good. And we are kind of almost done with this chapter. So far, we are not going to cover Doppler for now, Doppler effect for now, nor polarization. Okay, we're going to skip them for now. If we have time, we'll return to them. And what is going to come next is going to be geometric optics. And for now, so let's go back to our syllabus here. Chapters 20 and 21 was for exam 2, right? So we have, so far, we have covered all those 3 chapters for exam 3. Let's here you go. Induced electromagnetic, electromotive force, blah, blah, blah. Okay, transformers. 1, 2, 3, 4, 5, 6, 7. Let's see if they have. Yeah, it looks like we have the right one. And AC circuits was in chapter 20 for the resistance, right? So you cover that. May or may not cover for now. Let us skip for now. Yeah, we didn't do that. But don't think it's not important. It is important. This one definitely will not cover. We're going to skip the last two chapters, and that's what we have so far for the exam 3. Okay. Plus, for material so far, the material for exam 3 is plus labs 3 and 4, right? Labs 3 and 4. So we can stop right now, and if you have any questions, I'll be available here for my office hours. And let's not forget, we are not meeting. Let me see. We are not meeting on Wednesday, right? Because of the Genocide Remembrance Day. Let's confirm that. 2 more minutes. We still can do that. Let's see. Let's confirm that this is the right date for the holiday. Even better. Let's see. Calendar. No, that's not what I want. Okay, I want this one here. Academics. Program, schedule and catalog. Fall, spring, let's see, spring 225. Holiday. Let's look for the holiday here. Holiday. Last day to let's see. Where's the holiday? Memorial Day, Genocide Remembrance Day, Thursday. Genocide. 24th? Oh, something wrong here, isn't there? Where? Huh.
Professor,
Okay.
I believe that day was on Thursday last week.
Yeah, that's right. It was Thursday last week. Okay, so I have to adjust my yeah, okay, I know why I made that mistake. Okay, so you do have a class. Okay, let me correct that. Oh, that's so good that we do that, right? So we don't make a mistake. We do have a class on Wednesday. There's gonna be a lab. Okay, I will correct that. And I'm going to lab 05. I will send a message to you all. Okay, we do meet, class meeting. Okay, so I see you the day after tomorrow. Okay, see you. Bye bye.
Thank you. Bye, Professor.
Welcome. Bye bye.
Have a good one, Professor. Take care.
You too. Bye bye.